Hello and welcome once again to the Waters and Stanton video channel. We're running up to Christmas 2023, but of course if you're watching this a few weeks later it'll be 2024. Either way, we're going to cover some news items, and also I'm going to look back on the end-fed half-wave antenna, an antenna that has really revolutionised antenna design in the last few years, and certainly enabled a lot of hams to get on the air and operate on bands they wouldn't otherwise be able to operate on. But there's been some interesting developments, so let's go through some of these as well and bring you up to date on the end-fed half-wave antenna. About a year ago, Yaesu released the FT710 AESS. I think some of us thought this was a cut-down version of the FTDX10. It certainly isn't. And this was followed later in the year with the release of the FT710 Field. We'll be taking a look at this radio. It's actually quite a remarkable radio, and we'll be covering it in an upcoming video. Here at Waters and Stanton, we're pleased to advise you that we're launching a brand new website. It's going to be faster and more slick, and by the time you watch this video, it may well be in operation. ICOM have announced the release date of their new ICR15 scanning receiver. We understand it's going to be released in spring of 2024. It covers 108 to 500 MHz, AM, FM and wide FM. It's IPX7 rated. That means to say you can use it in the bath. Why would you want to use it in the bath? Well, apparently you can listen to the FM broadcast bands, but at the same time be monitoring the VHF and UHF air bands. And as to the price, well, that hasn't been fixed yet, but as soon as we know, we'll let you know. So the end-fed half-wave, that's certainly an antenna that has become very popular over the last few years, and I've covered it in a number of videos, but I thought it'd be good to look at some particular topics that keep coming up and perhaps bring you up to date on the latest developments. But first of all, let's look at the counterpoise situation. Do you need a counterpoise? Well, yes and no. Any antenna that's fed with coax cable has really got two poles, and in the dipole you've got the either side of the centre. When it comes to an end fed, well, you do need a sort of counterpoise, but you don't. Let me explain. It's been established by Lesmox G6XM many years ago, and more recently there's been a number of articles, the latest one in CQ in December 2020, I think it was. And the consensus is that you need a counterpoise, but it only needs to be 5% of a wavelength. So what's 5% of a wavelength? Well, on 80 metres it's 4 metres long, and on 40 metres it's 2 metres long. And the outside of the coax, the sheathing of the coax, can act as that counterpoise. What you do need to make sure is that you've got a line isolator after that short length of coax cable. I've found in actual fact that all you need to do is to have a line isolator at the point where the coax enters the transceiver or the VSWR meter, whichever there's a first thing in line. So the counterpoise really takes care of itself. You don't need a separate counterpoise. I've tried it with a separate wire. It makes no difference at all, and the consensus is now pretty unanimous that the coax outer sheathing will do the job. And as I say, if you've got a 40 metre base antenna, the base frequency is 40 metres, then you just need a 2 metre counterpoise, which is taken care of on the coax sheathing. And if it's longer, as the coax probably will be, that doesn't really matter. Just make sure you've got a line isolator. And do remember, one of the advantages of an end-fed half-wave is the feed point is often very close to the shack, so the loss on that coax feed line is very low indeed. My favourite way of making a line isolator is to get a ferrite core. This is 240-43 material, and wind about 7 or 8 turns of coax around the perimeter of the core. That seems to do the trick. Here's one I use on an outside antenna system, and It's pretty crude, but it does the job. And if you want to check your coax loss or carry out any other antenna measurements, you can't do better than getting one of the Rig Expert antenna analyzers. We stock the complete range, and all our versions are the Bluetooth versions. Well, let's now turn our attention to the UNUN, the 49:1 UNUN. It's a universal transformer, isn't it? 49:1 UNUN. Everybody uses it. But is it right? Have we got the design right? Now, Colin, MM0OPX, has got a YouTube channel. Check it out. He's done some interesting experiments on the design of matching transformers for end-fed half waves. It's not quite as straightforward as you might think. He's tried different materials that give improved VSWR or extend the frequency coverage. He's also tried changing the ratios. So it's not quite straightforward as you may think. Now, in a CQ article back in December 2020, he decided that the best ratio was 36:1. I mean, you can go 36:1, 49:1 or 64:1. But he found that 36:1 was the best ratio. But the ratio really depends on the impedance at the end of the half wave, and the impedance at the end of the half wave is very much determined by where it's situated. For example, if you have an end-fed half wave running horizontal down the garden, it will be a fairly high impedance. It could be around about 2,500 ohms, 3,000 ohms, something like that. But if you were to erect it as an inverted V or an inverted L, the feed point would be near the ground. And the impedance of an end-fed wire is very much affected by the proximity of the feed point, because that feed point is voltage, high voltage, and that part of the antenna is very, very susceptible to the relationship to ground and fences and etc., etc. So it may well be that if your feed point is fairly near the ground, the impedance is lower and that you need a different ratio transformer. So it's not as simple as you might think. Now let's look at the winding of an UNUN. Of course, you can buy commercially made ones, ready boxed and so forth, and that's great. But there is an attraction in making your own, and actually financially there's an attraction in making your own if you can. And it's not that complicated actually, because I think we're all used to UNUNs and BALUNs being multi-winding affairs, and you've got to make sure which colour goes where, etc., etc. But with this sort of transformer, it's very, very easy. Let me show you a picture of one that I've made, and I've done some videos on this particular design. You can see it's fairly straightforward. Now, the conventional design uses enamelled copper wire and a couple of wires twisted around to couple the primary, or make the primary and the secondary. Well, I've done away with that idea. I found about a couple of years ago now that you could use the auto transformer principle. So you've just got a single winder and you just tap up from the earth point up 2 turns to give you the ratio that you need. So in other words, if you wound 14 turns on the core, you tap up 2 turns and you've got the necessary 49:1. So you've got 14 turns, you tap up 2 turns, so you tapped up 2 turns, 14:2 is the same as 7:1, 7 7s are 49, you've got your 49:1 UNUN. But it's even simpler than that, because you don't need to use enamelled copper wire. A ferrite core is non-conductive, so you can use tin copper wire, which I've done. That makes soldering even easier. Now, going back to the article that was published in CQ magazine 2 years ago, WA5VJB found that in fact you can improve the matching system by coupling at the centre of the winding. In other words, not coupling at the bottom of the winding, but coupling at the centre of the winding. You had a winding around the perimeter of the ferrite core, and you had a 2-turn coupling at the centre. I haven't tried that, but he says that that improves the matching situation. So we've got all these possible variables, but they're just variables. They don't make dramatic difference. Sometimes they make construction easier, of course. If we just take a break for a minute. Now, this morning I worked Brian's ZL3XDJ on 40 metres, and it was a grey line DX contact. And what it really encouraged me, and hopefully you, is that you don't need a fantastic antenna system to work DX. I was using a half-size G5RV, which at the moment is down around about 20 foot above the ground, so it's pretty low. And you would think it would have high angle radiation, which it probably has. But I managed to work Brian ZL3XDJ. We started off at, I got a report of 229, and he was just about readable. But as the QSO built up, and only over a few minutes, my signal increased, and eventually I was almost 559 with him, and he was certainly 559 with me. Now, the interesting thing is that Brian is very much a basic amateur. He's an XG station, his call sign was G4XDJ, and he's got a YouTube channel. I'll just put a clip up now from his YouTube channel, but I encourage you to click on to his YouTube channel, and perhaps this particular YouTube video, because it just highlights the fact that you don't need phenomenal antenna systems to work DX. You need a bit of patience, sometimes a bit of luck, but it's more patience than luck. So take a look.
Just doing a short video about a very interesting and surprising QSO I had, in the sense that we all love to get QSOs with signal reports of 5959. Here we've got a very good DX QSO, which I enjoyed thoroughly, and it unfolded and surprised me as we went on. A weak signal there. Just slow the CW speed down to suit him. I think it was a Mike 0 station. My mistake. Mike 0 Lima Romeo Quebec. Give me a 5, 5 and 9. LRQ. And the name is Peter.
The signals are not strong, as you can hear, and it's got that typical DX sound to it, but it's readable. So quite impressive with the station in the UK using a loop antenna and a distance of 1,300 miles. Very impressive. So there's a lesson there somewhere. Well, there we are. I'm sure that Brian doesn't mind me showing you that clip. And it's an interesting little clip anyway, and it proves that simple antennas can get you DX. Just needs a bit of patience and perhaps a bit of skill. Now let's return to the end-fed half-wave antenna. One thing you will notice is that it's a little bit shorter than it should be. In other words, if you measure out half-wave length of wire and you connect it up to your 49:1 unknown or whatever transformer you decide to use, or whatever ratio you try to use, you'll probably find that it's low in frequency. And that's because the transformer, when it's connected to the end of a half-wave antenna, it actually loads it slightly, because the end of a half-wave is very, very sensitive, and as soon as you connect a transformer to it, it'll lower the frequency a bit. So you'll find that the antenna actually needs to be shortened by perhaps on 40 metres about a metre or something like that. Trial and error, of course, but at least you'll have to shorten it rather than lengthen it. Now, let's talk about the actual antenna itself, the actual wire. We know that a half wave works on its harmonics, but unfortunately what it doesn't do, it doesn't have a direct relationship with those harmonics. You'll find that as you go higher in frequency, the relationship between the fundamental and the harmonic is not perfect. What actually happens is that the resonant frequency on the higher bands becomes progressively higher within the band. For example, you have a 40 meter antenna which is resonant on 7 megahertz, and you would expect that on 14 megahertz it would also be resonant. Well, it's actually not. It starts to creep up. It's probably around about 14.2 or 14.25. And then when you get to the 15 meter band, 21 megahertz, you'll probably find that it's almost out of the band. And on 28 megahertz, it's right at the top of the band, if not out of the edge of the band. So there's not a direct relationship between the fundamental and the harmonics. The frequencies tend to creep up. The classic way of correcting this was to add a small loading coil around about 2 meters in from the transformer. And you've probably seen this on commercial designs. They have about a 4 or 5 turn little inductor with about probably about 2 centimeter diameter coil. Well, it's been found that that is not the best way to do it. The best way to do it is to add a capacitor, what we call a loading capacitor. And if you insert a capacitor in a length of wire, what actually happens is that it actually raises the frequency on the lower bands and progressively has less influence on the higher bands, which means to say that if you insert a capacitor, say you've got an 80 meter antenna that is resonant on 3.5 megahertz, well, quite clearly when you get to 10 meters, because of this progressive increase in frequency, it's going to be resonant around about 31 or 32 megahertz. So this coil helped it, but it didn't help it enough. And it's been found that a capacitor has the effect. So if, for example, you insert a capacitor in the 80 meter half wave antenna, you can actually raise the frequency of that bit of wire by trimming it to resonate on around about 3.65 or 3.7. And that capacitor has actually had a major effect on 80 meters, but it has less and less effect on the other bands. So what actually happens is you tend to reduce the frequency on the higher bands. So inserting a capacitor means to say that the actual creeping of the frequency on the higher bands is almost eliminated. And it's also been found that the best place to put that capacitor is actually 32% in from the feed point. And in this particular article in the CQ magazine a couple of years ago, they recommended 150 picofarad capacitor, 32% in, will actually have the effect of enabling you to resonate the antenna at around about 3.7 megahertz on 80 meters, and the harmonic relationship will be pretty well preserved as you go higher in frequency. Now I've put up on the screen here the dimensions for the 80 meter version, and you can see the 150 puff capacitor in line. And I'll just zoom in a bit so you can get the dimensions. Now this trick also works pretty well on a 40 meter antenna, and I'm going to put up on the screen now the diagram of a 40 meter antenna that appeared in the CQ magazine, and they actually placed the capacitor in the centre of this antenna, and it actually does preserve the harmonic relationship much better than if it wasn't there. So it's well worth considering. As regards the voltage rating, well, you need something with the little stand a few volts. I would say that on the 100 watt transceiver or 100 watt output transceiver, you'd need something like 1 kV capacitor, which is not too difficult. You can get those. But also, of course, you can either series or parallel capacitors up to increase the actual rating of the capacitor. So bear that in mind. You could, of course, also create a capacitor using a coax cable, but you'd need a reasonable length of coax cable. I think there's a guideline. RG58 is about 25 puff per foot. So to get 200 puff, which I think they want in this particular case on 40 meters, you'd have to have You'd have to have about 8 foot of RG58. It's entirely possible, and you could coil that up. Well, the coiling up won't have any effect at all. So you might consider that as an alternative. So in summary, the end-fed half-wave antenna is a very, very good antenna. It's very docile. You can bend it around. It doesn't seem to matter too much. Obviously, if you bend it around a bit, then you'll find that the resonant frequency will change slightly. But if you add this capacitor, you should find that it works very well on all the bands. There is a bit of experimentation there, but I think what have we found? Well, we found that the 49:1 UNUN is not necessarily sort of cast in stone, but it's a good starting point, and most people find that 49:1 UNUN works. The antenna is going to be a bit shorter. As to the winding of the UNUN, you can easily make your own if you get a ferrite core. You don't need enamel copper wire. You can use tin copper wire because ferrite is not conductive. And you can use the auto transformer method, which is very simple to use. And you don't have to have that crossover point, because if you look at a lot of diagrams, you'll see the winding goes sort of 6 or 7 turns, then it crosses over and goes back on itself. It's also been found that there's no real benefit in that, so don't worry about that either. And it's altogether a pretty flexible design. So if you've got a soldering iron, and if you can get a bit of wire and get one of these ferrite cores, then it's worth getting. The ferrite cores are not cheap. I mean, a 240-43 maybe costs you about £10 now, but it's going to last you. Just don't drop it on the floor, because it will. It's like china; it will break. I've broken one, and that's £10 down the drain. But anyway, it's worth getting, and you'll have a lot of enjoyment out of it. So there we are. I hope this has been helpful. As I said, we're shooting this video just around about Christmas time, so I should wish you a very happy Christmas, and thank you for your support on this channel. It's been a great year for us on this channel, much appreciated. And also thank you for your support at the shop, because we've had some very nice comments from customers, and as I've said several times now, we've been going for 50 years. Gosh, it feels like it sometimes as well. Anyway, as I say, thank you for your support on this channel. You take care, enjoy your ham radio over the holiday period, and I'll look forward to seeing you in 2024, but I might slip an extra video in just before then. And if you're watching this video 6 months down the line, you think, what are you talking about, Christmas? It's summer now. That's something we can look forward to, isn't it? Summer. Thanks for your support. Much appreciated. Take care. See you in the next video. Bye for now.